Chapter 3 on Relative Growings. All through the calculus, we are dealing with quantities that are growing, and with rates of growth. We classify all quantities into two classes, constants and variables. Those which we regard as of fixed value and call constants we generally denote algebraically by letters from the beginning of the alphabet, such as A, B, or C, while those which we consider as capable of growing, or as mathematicians say, of varying, we denote by letters from the end of the alphabet, such as X, Y, Z, U, V, W, or sometimes T. Moreover, we are usually dealing with more than one variable at once and thinking of the way in which one variable depends on the other. For instance, we think of the way in which the height reached by a projectile depends on the time of attaining that height, or we are asked to consider a rectangle of given area and to inquire how any increase in the length of it will compel a corresponding decrease in the breadth of it. Or we think of the way in which any variation in the slope of a ladder will cause the height that it reaches to vary. Suppose we have got two such variables that depend one on the other. An alteration in one will bring about an alteration in the other because of this dependence. Let us call one of the variables x and the other that depends on it y. Suppose we make x to vary, that is to say, we either alter it or imagine it to be altered by adding to it a bit, which we call dx. We are thus causing x to become x plus dx. Then because x has been altered, y will have altered also, and will have become y plus dy. Here the bit dy may be in some cases positive and in others negative, and it won't, except by a miracle, be the same size as dx. Take two examples. 1. Let x and y be respectively the base and the height of a right-angled triangle, pictured in figure 4, of which the slope of the other side is fixed at 30 degrees. If we suppose this triangle to expand and yet keep its angles the same as at first, then when the base grows so as to become x plus dx, the height becomes y plus dy. Here, increasing x results in an increase of y. The little triangle, the height of which is dy and the base of which is dx, is similar to the original triangle, and it is obvious that the value of the ratio dy by dx is the same as that of the ratio y over x. As the angle is 30 degrees, it will be seen that here dy by dx is equal to 1 over 1.73. 2. Let x represent, in figure 5, the horizontal distance from a wall of the bottom end of a ladder, AB, of fixed length, and let y be height it reaches up the wall. Now y clearly depends on x. It is easy to see that if we pull the bottom end A a bit further from the wall, the top end B will come down a little lower. Let us state this in scientific language. If we increase x to x plus dx, then y will become y minus dy. That is, when x receives a positive increment, the increment which results to y is negative. Yes, but how much? Suppose the ladder was so long that when the bottom end A was 19 inches from the wall, the top end B reached just 15 feet from the ground. Now, if you were to pull the bottom end out 1 inch more, how much would the top end come down? Put it all into inches. X is equal to 19 inches, y is equal to 180 inches. Now the increment of x, which we call dx, is 1 inch, or x plus dx is equal to 20 inches. How much will y be diminished? The new height will be y minus dy. If we work out the height by Euclid, then we shall be able to find how much dy will be. The length of the ladder is the square root of 180 squared plus 19 squared, which is equal to 181 inches. Clearly then, the new height, which is y minus dy, will be such that y minus dy squared is equal to 181 squared minus 20 squared, which is equal to 32,761 minus 400, which is equal to 32,361. y minus dy is equal to the square root of 32,361, which is equal to 179.89 inches. Now y is 180, so that dy is 180 minus 179.89, which is equal to 0.11 inch. So we see that making dx an increase of 1 inch has resulted in making dy a decrease of 0.11 inch. And the ratio of dy to dx may be stated thus: dy over dx is equal to negative 0.11 over 1. It is also easy to see that, except in one particular position, dy will be of a different size from dx. Now right through the differential calculus, we are hunting for a curious thing, a mere ratio, namely the proportion which dy bears to dx when both of them are indefinitely small. It should be noted here that we can only find this ratio dy by dx when y and x are related to each other in some way, so that whenever x varies, y does vary also. For instance, in the first example just taken, if the base x of the triangle be made longer, the height y of the triangle becomes greater also. And in the second example, if the distance x of the foot of the ladder from the wall be made to increase, the height y reached by the ladder decreases in a corresponding manner. Slowly at first, but more and more rapidly as x becomes greater. In these cases, the relation between x and y is perfectly definite. It can be expressed mathematically, being y over x is equal to tan 30 degrees and x squared plus y squared is equal to L squared, where L is the length of the ladder, respectively. And dy over dx has the meaning we found in each case. If while x is as before, the distance of the foot of the ladder from the wall, y is, instead of the height reached, the horizontal length of the wall, or the number of bricks in it, or the number of years since it was built, any change in x would naturally cause no change whatever in y. In this case, dy by dx has no meaning whatever, and it is not possible to find an expression for it. Whenever we use differentials, dx, dy, dz, etc., the existence of some kind of relation between x, y, z, etc. is implied, and this relation is called a function in x, y, z, etc. The two expressions given above, for instance, namely y over x is equal to tan 30 degrees and x squared plus y squared is equal to L squared, are functions of x and y. Such expressions contain implicitly, that is, contain without distinctly showing it, the means of expressing either x in terms of y or y in terms of x, and for this reason they are called implicit functions in x and y. They can be respectively put into the forms y is equal to x tan 30 degrees or x is equal to y over tan 30 degrees and y is equal to the square root of L squared minus x squared, or x is equal to the square root of L squared minus y squared. These last expressions state explicitly, that is, distinctly, the value of x in terms of y or of y in terms of x, and they are for this reason called explicit functions of x or y. For example, x squared plus 3 is equal to 2y minus 7 is an implicit function in x and y. It may be written y is equal to x squared plus 10 over 2, explicit function of x, or x is equal to the square root of 2y minus 10, explicit function of y. We see that an explicit function in x, y, z, etc. is simply something the value of which changes when x, y, z, etc. are changing, either one at the time or several together. Because of this, the value of the explicit function is called the dependent variable, as it depends on the value of the other variable quantities in the function. These other variables are called the independent variables because their value is not determined from the value assumed by the function. For example, if u is equal to x squared sine theta, X and theta are the independent variables, and u is the dependent variable. Sometimes the exact relation between several quantities x, y, z either is not known or it is not convenient to state it. It is only known or convenient to state that there is some sort of relation between these variables so that one cannot alter either x or z or y singly without affecting the other quantities. The existence of a function in x, y, z is then indicated by the notation capital F x, y, z, which is an implicit function, or by x is equal to f, y, z, y is equal to f, x, z, or z is equal to f, x, y, which are explicit functions. Sometimes small letter f or phi is used instead of capital letter F, so that y is equal to capital F x, y is equal to small letter f x, and y is equal to phi x all mean the same thing, namely that the value of y depends on the value of x in some way which is not stated. We call the ratio dy by dx the differential coefficient of y with respect to x. It is a solemn scientific name for this very simple thing, but we are not going to be frightened by solemn names when the things themselves are so easy. Instead of being frightened, we will simply pronounce a brief curse on the stupidity of giving long, crack-jaw names, and having relieved our minds, we'll go on to the simple thing itself, namely the ratio dy by dx. In ordinary algebra, which you learned at school, you were always hunting after some unknown quantity which you called x or y, or sometimes there were two unknown quantities to be hunted for simultaneously. You have now to learn to go hunting in a new way, the fox being now neither x nor y. Instead of this, you have to hunt for this curious cub called dy by dx. The process of finding the value of dy by dx is called differentiating. But remember, what is wanted is the value of this ratio when both dy and dx are themselves indefinitely small. The true value of the differential coefficient is that to which it approximates in the limiting case when each of them is considered as infinitesimally minute. Let us now learn how to go in quest of dy by dx.